Let's talk about magnetic fields and wires that are carrying electric current. So in this illustration here, I have two wires, which are the lines, carrying some current. And so in this case, we have current that's flowing in the same direction for both of these wires. Okay, well, let's take this kind of one step at a time, where we have, let's look at the magnetic field that is produced by the first wire's current. So I'm going to keep all this in the same color. So to figure out what magnetic field is produced by this current, we use the right-hand rule, so thumb in the direction of the current. And so that means that our fingers are going to curl up on the top, and then down on the bottom. I should probably draw these fairly symmetrically. And ideally, I would do a much nicer job of these circles. Okay. So what does that mean for the second wire? Well, it means the second wire has this this downwards magnetic field surrounding it. And so we can ask ourselves, well, what force will a downwards magnetic field have on this wire? And so, well, let's take a look at how that works. We're going to end up with, of course, a force that is the result of the cross product between the current and the magnetic field. So we're going to end up with a force that is upwards. So that is going to bring that second wire closer to the first wire. But let's unpack that a little bit. Okay, so we have some wire with a current. And so within that, well, what is an electric current? Well, really we have these charge carriers that are traveling at some velocity inside here. So we've got some dq inside this little segment of wire, and they're traveling at some v at that moment in time. I'm not too happy with that arrow. A little better. Okay, so in this case, you know, we imagine that there's some velocity here, and then there's going to be some magnetic field that is 90 degrees from that. Okay, so let's go back to our equation for the force that is caused by a magnetic field and apply it to this situation. So we've got this velocity cross the magnetic field. Now what's going to happen here is that instead of dealing with the force and the Q at first, we're going to think about this in terms of a little piece. So we're going to have a little dF. This is the force by the magnetic field on some little dq. And then the velocity in this case is actually technically going to be the drift velocity within that wire. And so now we want to start putting this in terms of things we know about the current. Turn it into something that's in the language of this specific situation. And so what we're going to do is we're going to substitute in for the dq, because we've got our current, which is equal to dq dt. So it's a rate that we have a flow of charge. And so because of that, our dq can be written as I dt. Now next, what I'd like to do is put the velocity in terms of something that is more measurable across this wire, which is the distance. So our velocity is of course equal to distance over time, and so we have the velocity is equal to d, I'm going to say dl in this case, because L is some arbitrary distance, along the wire. And so now we can say, well, our velocity dt, which is in our equation at the moment, is equal to dl. And so we substitute that in, and we get df is equal to I dl cross our magnetic field. And L has a direction. It's a vector. So, so what we're going to do now is we recognize, what is this? Well, this is the force at that point that we noted on our diagram here. To find the force on the whole wire, which is really what we're interested in, we have to integrate. Now, if you integrate, what you end up getting here is a force that's equal to the current, the distance here, the L, and the B. And there's no sign. There's no sign term because the angle here is 0. Okay, so that's a little dive into how the current of the adjacent wire is creating a force on this second wire, because the current is producing a magnetic field, and that magnetic field is producing a force on those charge carriers in the electric current. In fact, there's going to be a force on the first wire by the second as well. Okay, that's it.